Okay, the problem is saying Laverne is a rancher who would like to construct a corral along the north side of the river. No fence is required along the river. The west side of the corral is adjacent to the neighbor's property, who has agreed to evenly split the cost of the fence along with the west side of the corral. If Laverne would like to spend no more than, here we go, $2,550,000 on the project, and has determined that the full cost per foot of fencing is 100 per linear foot. Determine the dimensions of the corral of the maximum area given the cost constraint. Okay, so we're given a cost of the corral already, and this is how much we want to spend, 2,550,000, and each linear foot is 100 feet per linear, $100 per linear foot. So if we come up with an equation for that, we're saying the total cost is equal to adding up x plus y, and each of those are being multiplied by $100, right, per linear foot. But there's a little addition here because the neighbor right here agreed to split evenly the cost of the fence along the west side of the corral. So this side here is going to be half the price. So let's go ahead and edit this one real quick, and we'll call this the 1/2 here, right? Because that'll be kind of half the cost because we're cutting distance in half, cost in half. Okay, so we have the total cost, which is 2550000 is equal to, we can add those together to be 3 over 2x plus y. We multiply this by 100. And no, I'm just going to go ahead and divide that 100 over. And this would be 2550001, right? We got rid of 2 of the zeros, is equal to 3 over 2x plus y. Okay, so but maybe that'll be helpful for us later. And then our goal is to maximize the area of the corral. And the area looks like it's a rectangle, right? So area of rectangle, area is equal to length times width, times width. And so our area equation here is just x times y. Okay, now our maximizing equation here, our optimization, is we're going to take the derivative of area because that's what we want to maximize. But as you can see, there's two different variables here. So let's go ahead and swap one of these for the other. We have an option here. We can either solve for y or solve for x. In this case, it's probably easier for us to solve for y. So let's get y is equal to 25500 minus 3 over 2x. And we're going to go to plug that in here. Area equation is equal to x times 25500 minus 3 over 2x. We can go ahead and distribute that to be area is equal to 25500x minus 3 over 2x squared. Okay, let's go and optimize it. We take the derivative, set it equals 0, looking for those critical points. The area prime is equal to 25500 minus the 2 comes down, right? Gets rid of the fraction. So we're left with 3x, and then 2 minus 1 is 1 for the exponent. Okay, we're going to set this equal to 0 to optimize it. And we end up with negative 3, x equals to negative 25500. X equals to negative 25500 divided by 3 on negative 3. So that becomes a positive number. X is equal to 3 goes into 25. 8 times 15, 500. Okay. So that's our x value. So let's go ahead and solve for the y value. Our y value is, if equation is equal to 25500 minus 3 over 2, 8500. Okay, 25500 minus 3 times 4250, and then we multiply that by 3, 25500 minus, was it 12,750, and then if we subtract those together, y is equal to, wasn't that just half? 25500 minus, yeah, 12,750. 750. That was half. Okay. So our x, okay, so determine, reading up here, determine the length of the east and west sides. So we said that was our x value, so that's 8,500 feet. Our length that's parallel to the river, that's our y value, that's 12,750. And then to find the area equation, right, we multiplied our x times our y, which is going to be 8,500 times 12,750. Let's do that on the calculator. 0 times 12,750 equals to 108,375,000. Okay, that's a lot of square feet.